much better than density. But you see, everything has a distribution. What I am plotting is there is a distribution of tetrahedrity, distribution of bonds. So it's a lot of work. And here's the static structure, which is how packing is there, and packing becoming more and more crystalline as they go to lower temperature. So growth of tetrahedral structure, large difference in liquid structure below. If you go below 230, 300 to 250, not much. But as you go below 230, things change very quickly. You can look into one more thing. Water, you know, can make 4 hydrogen bonds, undergraduate oral question we asked. But there is a distribution. Not all are 4. Some are 5, some are 3. What happens as you lower the temperature, number of 4 coordinated increase. Remember, rate is constant pressure. Let us do a constant pressure, only constant volume. Is not realistic, but it's a reference gives us. The constant, because the reason constant volume doesn't show the anomaly, because fluctuations are suppressed. You know, water density has to fluctuate. You know, like, you know, specific heat is given by, the definition of a specific heat is Cp enthalpy fluctuation. This is the specific heat with certain temperature. But this is the specific heat, definition of a specific heat. Cv is delta E square. These are called linear response theories. Sometimes when I like to give these talks, I want to kick the professor or faculty out so that I can talk to the students. Now, these are beautiful definitions of the specific heat. And I always believe in 2 or 3 students understand what I am talking, that's worth it. Now, what happened at Cv, you don't have the volume fluctuation, but much of the anomaly in this water business is because of these fluctuations in local density and volume, as you will see. And I tell you again and again, this is as fundamental as it gets. Okay. So these are now we are going to go into some results, and as I told you, these simulations are really old. Okay. Now, not only specific heat, I can define a frequency dependent specific heat. There is the exact definition of frequency dependent specific heat, and we will introduce here what is frequency dependent entropy. That's a little later. Frequency dependent specific heat, I can define why. I can define when there is one component of the fluctuations. So this is enthalpy fluctuations, but these fluctuations happen with the time. I can talk of delta H0, delta Ht. I can talk of delta E0, delta Et, time correlation of the energy, and Fourier transform of that gives me frequency dependent, and that allows me to decompose. I'm breaking things up into small parts. That's called Fourier analysis. I'm doing a Fourier analysis on the fluctuations in the hope that will tell me what is happening in microscopic level. And what is happening in microscopic level is clearly shown here, that this is the imaginary part of the frequency dependent specific heat. You can see at high temperature, which is just this one, just like a libration, maybe little bit, but then as a lower temperature, 300 Kelvin or so, it becomes like that. So they go to lower and lower frequencies. Look at 220 Kelvin. From 230 to 220, it really, this picks up, shifts to lower frequency. That means a large number of slow collective fluctuations are appearing in the system. Very slow modulations. These density fluctuations, because this spectrum shifts into lower. Look at the real part of the frequency dependent specific heat. It rises, it shifts, and it rises. Okay. However, from 220 to 205, there is a huge transition. After rising, as I cross 220, it falls down. As I go below 220, it shifts to slower, but at the same time, amplitude of the fluctuations goes down. Okay. This can be understood. There are definitions given here if you want. This one paper has been published, and that is the one which, again, after 3 rounds got out from Nature, and we put it to JCP. So in this field, you try to always go to those journals. But one can show that what is happening is an H bond, hydrogen bond network dynamics. Okay. So now, again, this is the specific heat. Again showed little bit more detailed constant CV. CV also shows similar character but lower extent. This is CP, this is CV. And then a little bit detailed analysis you can show, and you can show the real part is agreeing. It is one can show that our simulations and theoretical analysis agrees exactly with the experiment. Okay, that can also not too surprising. So what is that happening there as you go towards 220 or close to 220? What happened? These long range correlations appear in the system. Correlations now, and this is another called two-dimensional spectroscopy. What we have plotted is the temperature correlation, wave number and frequency dependent energy or temperature fluctuations. High temperature, it is low frequency. This is frequency, this is wavelength. So as I lower the temperature, as you lower the temperature, low frequency fluctuations come. Low frequency and longer correlated fluctuations come here. Look at this peak. Here everything is localized. Here they are delocalized. Here they are of the nearest neighbor level. Here of up to 6 nearest neighbor, the fluctuations come. And this is shown here. What is the contribution to energy fluctuations of a given water molecule? At high temperature, everything is nearest neighbor, which is the rate. But at low temperature, much of it is second shell. Then you go to third shell, you go to fourth shell, contribution. So things are becoming correlated. Things are becoming connected. As I tell you, these are as beautiful in phase transition, critical phenomena, or whatever you think of, they come. So temperature dependence, relaxation time of hydrogen bond network dynamics. Hydrogen bond network dynamics you find out by saying, okay, what is the lifetime of hydrogen bond, and you find the time position function of that. So that now in picosecond and what about temperature. So at high, this region is high temperature. High temperature, it is growing almost like Arrhenius. Then it becomes what we call super Arrhenius, that is stronger than Arrhenius. But then there is a break. Around 220 Kelvin, this one would have continued. Water goes to a different structural entity. This is what we call a multiple transfiguration. That is, it goes over to a different thing. There is a dynamical transition to 220 Kelvin. That's not too surprising. As I said, I am not too interested in that. Lot of work has been done in that, but there is a movie here, probably it will not work. No. Okay. That's why one should not one's opponent. So what is shown here, at 250 Kelvin, you are mostly high density liquid. The normal liquid that we say is a high density. That density is 1 or very close to 1. As you go to lower temperature, remember ice is a density 0.92 in our scale of water density 1, which is the universal scale. And on 220, the movie would have been working, would have been able to see this red is high density, blue is low density. You would have seen large density fluctuation between high and low density. You would have seen that at 220 Kelvin, a box, this is called coarse-grained description. I have taken each box, divided the system into 27, 3 by 3 by 3, and then each there I calculated the average density parameter and average density and assigned him which is a high density liquid, which is a low density ice-like liquid. You would have seen there are very rapid fluctuations going between red and blue. Then if you go, it's really becoming very quiet and everything is ice-like. Here it is not crystalline ice. Amorphous ice-like it becomes. There is a lot of disorder, and I will talk of that disorder. There is a local tetrahedrality, but that does not propagate like they propagate in ice. But these beautiful fluctuations that happen between low density and high density continuous, not at a local scale, but a coarse-grained scale, where you have this 2-3 nearest level is the responsible for this. This again I am saying it is not. This system is divided into 64 boxes. 16 molecules in a box in the average, or 4 by 4 by 4, you also did 3 by 3 by 3. This, when you go to 2 by 2 by 2, when you make 8 boxes, you see these fluctuations go ahead. So fluctuations are local, but not too local. These are very rich area, as I am saying. Many things, I keep telling it of that, there are many things I am not going to explain to you. Okay, now, as I said, that this thing has created tremendous amount of controversy internationally. Many different ways of things have come. So I always, my favorite IACS poem that blind maid and the elephant, and then we tell a little bit of this. It was 6 men of Hindustan to learning much inclined who went to see the elephant, though all of them were blind. This is like Lewis Carroll. You know, Lewis Carroll, you have done the carpenter and the carpenter, what is the name of BA? Okay, whatever. The same kind of thing. That each by observation might satisfy a case. So they made an elephant. They first approached the elephant and happening to fall against the broad, and then at once he began to bawl. God bless me, but the elephant is very much like a wall. Then the second guy goes and sees the task. And so it is round and smooth and sharp. Then it's like a spear. Another guy said it is like a rope. This particular problem of our, to entertain you a little bit, I have given the elephant and the diamond is the pictures. Internet is full of these things. Is very, so in this case of water, everybody has a theory and almost everybody has their own view, and it is not settled. But still remains enormous amount of fascinating properties there. Okay, so right now I am again continuing to tell you what is our picture of these anomalies of water. So our picture is that when you go to 50 Kelvin, then there is a long regions of high density. Deep blue is high density liquid, which is mixture of 4 and 5 coordinated and 3 coordinated defect liquid. That's what our room temperature water. That's a defect as compared to ice. But when you go low temperature, they become more and more. This is Cp and Cv. Okay. But this is both are almost the same, but I think Cp and Cv. Okay. Now if you go to 205, this is constant volume. If you go to 205, then what you see is very interesting. You see now high density liquids with 3 or 4 coordinated are islands, but it is a low density, still defective, that perforates the system. So it seems these fluctuations between low and high density, which gives rise to anomaly and gives rise to this kind of departure. Cv has no transition, but at a constant pressure you have these multiple transitions, which are because of the perforation. That means the high density clusters break off and low density clusters pervade the system and perforate the system. There is one more thing here, that we got the frequency dependent of dielectric relaxation is the more common. That again shows very much like frequency dependent specificity. The emergence of slow dynamics, much slower dynamics than high temperature, and that agrees quite well with the experimental results. This one is 300 Kelvin and these are the experimental 300 Kelvin. We have compared our data with the experiment, and and you cannot, you can see you cannot go below certain temperature here. Again coming back, now I just want to spend a little bit more time on something which I have not talked before, that what is the temperature dependence of the relaxation time. I can get the relaxation time by dielectric relaxation, I can get the relaxation time by frequency dependent specificity, I can get the relaxation time hydrogen bond dynamics, I can get from n number of different ways. And or structural relaxation time from dynamic scattering, dynamic scattering, dynamic structure factor, and all of them show the similar behavior, almost the universality. High temperature from 300 Kelvin, this is 1 over temperature, to 220, you have this branch, and that branch I show you becomes, the liquid transforms to a different branch at 220 Kelvin. Okay. So this region is the region that we know in our ordinary experience of supercooled liquid. Most liquids behave like that. Most liquid is, we call them fragile liquid because of the departure from Arrhenius behavior. But most liquids go like that, then they diverge and go over to glass, not water. Water does not go to glass like that. And one more figure I will use very soon. It undergoes multiple transfiguration, and so 220 Kelvin. This is now this water that we drink. That is that water. That water continuing like that, and then would have diverged. But the real water, we believe, undergoes a structural transformation and goes to a different branch. Then it undergoes one more structural transformation before it goes to amorphous ice state. And this is the mechanism of that one is trying to find out, that there is a no man's land which we don't know. Water, stable water, our water, it goes to supercooled, then this region is not accessible to experiment, and there is, I told you, there is lots of interpretation of what is going on here, lots of interpretation what is the reason for the crossover. One of them is considered the liquid-liquid transition, another says it is weakly first order transition, one more says what we believe in is there is a percolation transition, then there is something called singularity free interpretation. So there is a lots of very major paper on that. Now I come to this one, want to spend a little time, that what is really unique is amazing. So these ordinary liquid would have continued and relaxation time would have increased, and you would have got a glass transition around this region. What is a glass transition? Glass transition is defined experimentally as a point where viscosity becomes 10 to the power 12 Poisson. Okay? Or relaxation time becomes 100 seconds. That's what a glass transition, a laboratory scientist would say, that is the temperature liquid goes to glass. Like you do pentanol, you do octodaphenyl, many glass forming liquids are there which we routinely use, and they are almost all show that same characteristics. Very rapidly at certain temperature, 30 degrees centigrade below the glass transition, viscosity starts increase rapidly, relaxation time starts to grow, and it just goes to glass. After that it doesn't move. Not water. Water escapes the glass transition. Had it been here, relaxation time would have been much larger. This relaxation time would have been at this temperature would have been 2 orders of magnitude or so larger. This is a logarithmic scale. Not so. Now, so there is a rule, almost universal rule, followed by all the liquids. There are different kinds of liquids. They can be chalcogenides, they can be this phosphate, they can be orthotarphenyl, they can be this heteroalkali germanium oxides. All of them follow this beautiful rule. Glass transition by Tn is 2 by third. This is called 2/3 rule. So a liquid you can predict, if you know its crystallization temperature, you can predict its glass transition temperature is 2/3 of that. Not for water. Water completely deviates from that. Water you cannot put it on the graph. Water glass transition is about half. So if water would have followed this, I would have 2/3 to 73, that means near 180 Kelvin, water would have undergone glass transition. It doesn't do so. It continues to remain liquid. And this is shown what is happening in the picture, that so this is our normal liquid, then it undergoes a transfiguration to one more liquid, this continues to 220, then see how completely different they are, then it continues till it, it is beginning to that time scale that I was saying, it undergoes glass transition. Here in inset shows there is indeed a very sharp crossover. So we predict there are 2 dynamical transitions in water. One is 220 Kelvin, which people talked about. There is 195 Kelvin, which nobody has talked about. The new one is the reason that people, we are fighting with the referee. Referee agrees with the basic conclusion but wants to see much more data. Now these are plotted the potential energy of the per particle or per mole of the water and ice. This is ice. Look at that when I go to lower temperature, so this continues like that, and ultimately this 273 Kelvin, I go a little bit here, yeah, this is why it melts. It melts into water. This is ice, the blue one. But this is my supercooled water. So this one, water, ordinary water becomes supercooled. But look at the change of the potential energy. Then it's very interesting. Lower temperature, there is a 0.5 constant offset between the this is here glass. Okay, here is glass. There is a constant offset between the two. I'll come to this gas transition now. So now look at the entropy. Entropy is very dramatic. Entropy, it is a huge amount of calculation. Calculation of this entropy is just, taking 4-5 years to calculate the entropy. This is a high temperature water coming and lowering temperature. Entropy sharp falling rapidly, starts to fall rapidly. Then it undergoes one crossover here. And then it undergoes a second crossover here. Then entropy 110 Kelvin, maybe 120 Kelvin, entropy of ice and entropy of supercooled water or glass is the same. So this is the entropy of liquid minus entropy of ice in joule mole per Kelvin. This we know, we calculate it, we can measure experimentally measure it agrees completely with the theory and experiment with the ice, and there's a lot of work to do that. But important thing is that the entropy of water gives really very interestingly. This is the graph, is not just published, this is the one which we send to another major journal in just a few days time. Okay, so we try to understand it. What is this? We come back to that beautiful figure that I showed you, that how entropy behaves. Remember that, entropy and energy, because that determines the free energy now. Basic thermodynamics work counts for a huge amount of work. Now we looked into what very important, that what is 3, 4 and 5 coordinate water molecules doing. 4 coordinate water molecules, as a lower temperature, remember I am lowering temperature. 4 coordinate water molecules portion increases. 5 and 3 decreases. Okay. And they decrease at a different rate. But this one, this 5 coordinate one, decreases very rapidly. Now let me consider the geometry. This is something which Biman Bagchi, this should be rocket science. So 3 coordinate water molecules can be 2 types. One is that it can form 2 hydrogen bonds with 2 hydrogens and 1 with oxygen, but it can also form it this 4 coordinated. It can also form 3 hydrogen bonds. I will come back to later the 2 different stuff. It can form 2 hydrogen bonds with oxygen and 1 with hydrogen. That asymmetry